Let's look at question 11 in sample exam 3 Chem 11. This question actually is just about various ideas in quantum mechanics. A lot of it having to do with electron configuration or the Bohr model. So we're going to look through all of these questions one by one. It's just saying which of the following is true. It gives you basically three statements, A, B, and C, and then in D and E, there are options that refers to the previous three options in A through C. So let's take a look at A real quickly. I've attached a periodic table here for reference because we're going to need it to figure out the electron configuration of the first option. The first option says that nickel has an unpaired electron in its ground state electron configuration. Let's just write out the electron configuration of nickel. We look at the periodic table here, and nickel has 28 electrons. So, and of course you can go to the noble gas in the previous period, which is argon, as the starting configuration. And then afterwards you have 4s2, which is these two elements right here, and then 3d8. Now in order for me to see whether it has a unpaired or all paired electrons, I'm going to actually need to draw out the box diagram. So 4s would be like that, 4s2. 3d8 would have 8 electrons in the 5 3d orbitals. So 1, 2, 3, 4, 5, 6, 7, 8. So indeed, it has 2 unpaired electrons. The question specifically said it has an unpaired electron, and that's not true. It has 2 unpaired electrons. So that one would be wrong. Question B says the ground state of the hydrogen atom is more stable than the ground state of the beryllium 3 plus ion based on the Bohr model. Bohr model, if you remember, is one that has all these a proton in the middle, and then there's these orbits that are around it, and then you can have an electron, let's say in this orbit, and it can either fall or go up higher. And the orbit values are given in whole numbers, so it starts from 1, that's the closest one to the proton. That one is called a ground state, and then afterwards it goes higher and higher. And remember that we can calculate the energy of the electron, which is due to its attraction to the proton, using this equation, negative RH, that's a constant called the Rydberg constant, times z squared, which is the number of protons that appear in that specific ion or atom, and then times 1 over n squared, where n is the orbit number. So in the question, we're just being asked to compare the ground state of the hydrogen atom versus the ground state of the beryllium ion, and then decide on which one is more stable. So let's calculate it for hydrogen atom. The En in this case is going to be negative RH. I'm just going to use RH as a symbol here because it really doesn't matter what the value is because we're doing a relative comparison. Z for hydrogen is 1, right? Because there's only 1 proton in hydrogen. So 1 squared, and then divided by n squared. N squared is also 1 squared since we're talking about ground state in this case. So in other words, what we get is just negative RH. That will be the energy of the ground state electron in hydrogen atom. Then we'll look at the beryllium 3 plus ion. The energy of the ground state, n equals 1, would be negative RH. Now the Z is 4 for beryllium. If you look up in the periodic table, beryllium is right here, so that's 4. So 4 squared divided by 1 squared, since we're still talking about ground state. So what we have is negative 16 RH. Okay, so then the question is which one is more stable given these numbers? Well, remember that you can look at an energy diagram, and one of them has a value of negative RH, and the other one has a value of way lower than that, right, which is negative 16 RH. Okay, so the way we refer to something being more stable is if they're lower in energy. So that one would be the more stable one. And so that means that beryllium 3 plus is the more stable species. So the option that's given to us says that the hydrogen is more stable, so that's wrong because actually the beryllium is more stable. Let's take a look at the third one. It says for the hydrogen atom, the energy released when an electron from the second excited state travels to the ground state is that value. So that one is, again, back to the model, the Bohr model. So I'm going to just draw the orbits again. So here's the second orbit, say, and then here's the third orbit. Okay, and so it's saying that we're going to need to calculate the energy release when an electron goes from the second excited state. So you remember that this n equals 1 is called the ground state, and then n equals 2 is called the first excited state, and then n equals 3 is called the second excited state. So really we're asking about an energy transition that occurs when an electron from this level falls back to the ground state, which is the n equals 1. So it goes from 3 to 1. How do we calculate the energy change? Well, we use that delta E equation, and it's negative RH. Remember that Z is 1 for hydrogen, so it's just 1 over n final squared minus 1 over n initial squared. So to calculate it, I'm going to need the actual value of RH in this case, which is 2.178 times 10 to the minus 18 joules. Something you can find in a textbook if you don't have it in the question. And then times 1 over n final. The final value is 1, right? Because it's going back to the ground state. The initial value is 3 because it's the second excited state. So when we multiply that out, we get negative 1.94 times 10 to the minus negative 18 joules. And in fact, that's the value that we're given. So that means that C is the correct answer.